Hydrautomat. It's a water pump that uses exclusively water and air pressure to pump water from one level to a higher level. And I first found out about this device probably last year from a research website that would basically try to find old or lost technology, exotic technologies, things like that, and bring them to people's attention so they might be developed or put to use in the modern day. The Hydrautomat was actually first invented in 1921 by an engineer known as called Thomas Gaskell Allen Jr. He was a industrialist at the time and had no experience with the Hydrautomat, but he actually built this thing in his free time, and it was hailed at the time as an amazing engineering marvel that had a lot of promise for the world because it could be used to supply water for irrigation and other purposes. But for some unknown reason, it was used all the way from 1921 to probably around 1956, 1959, where it's last reported in, I think, some province in India is used for irrigation, and I didn't hear much about it afterward. Eventually, the company that made Hydrautomat was bought out by a company known as Crane Co., which is a fluid handling company, manufacturer of aircraft parts in Chicago, Illinois, but we don't really know why it's not used to this day. But I found out about this device and eventually figured out how it would work in general, and had very much to go by, because all I had was this pen illustration here. I know what the camera can see.
I'll get it.
Okay, that's fine. If you want to pass this around, that's what I had to go by. I didn't have any blueprint or anything. Just it's kind of a proof of concept we'll see on this sheet here. And eventually, though, even though I didn't have much experience with plumbing parts and things like that, I eventually went through trial and error, different prototypes, different designs, different developments of things, and came up with this arrangement here. Now, the way the Hydrautomat works is that it's a gravity-fed system that runs solely on water. So what will happen is you'll have, say, like a slope and elevation like a river running down a hill, or you'll have maybe a dam or water encashment or something like that. And what will happen is you'll have a high point, you'll have a low point, because if you have a slope, you have a high point and low point. And you would take the water in from what's called the feed tank here, and you would feed it down through this tube here called the inlet tube into this tank here called a operating tank. And what will happen is to start it off, what you would do is you would fill it up like it is right now, up to about this level. And then what I'll do is that I will let this thing fill up to the point that it actually trips this siphon here and starts to flow over. And what will happen is as the water is flowing from here into the operating tank and then flowing out to the siphon, what will happen is eventually it'll push out all the air in here, so I have a proper operation, and that cuts down any problems. And then what will happen is when this is flowing out, I'll turn off this valve, which will disconnect the water from the feed tank here to the operating tank, and the operating tank will start draining the water that's inside of it without being replenished. When this happens, what I'll do is the water will drain out of the operating tank and it'll pull the air down along with it, because there has to be something to fill this gap or whatever. So since something can't fill that gap, I'll just keep pulling the air down this tube here. And this tube is also connected to this here. I'll start pulling the air out of this tank, creating a suction as well. And what will happen is as this tank starts to drain more and more, it'll eventually create such a suction in here that's so strong that it'll actually pull water from this tank up this tube here into this tank up here to force a suction. And then what will happen is this will eventually drain out through the siphon, of course, and then the siphon will disable or whatever. And then what will happen is I can also optionally purge the air tube so there won't be any suction left in it, and then close it back up again, and then close off the siphon too, because sometimes there'll be an impulse reaction where if I open this too quickly, or if I just open this up, the water will go through here, straight out through the siphon and trip this without filling up the whole tank. Sometimes that'll happen. But I'll close this off right here, and then I'll open this up, and then when the water fills up, it'll take that air and it'll push it up. And since this tank here is filled with water, the air will push the water down. And since it'll pressurize the water, there will be check valves to prevent it from flowing back into this tank. And instead, it'll flow out through this tube and up into this open tank right here. And that's basically how the system works. It's kind of a two-phase system. It uses both suction and pressure. And now I'm going to demonstrate it. So, I'm going to close this, make sure. Then what we're going to do is going to start the suction cycle first, because we already have that going. Air bubbles out. Power's on. Yeah, okay. Okay, so now this is draining out right here. So I can turn off this inlet valve now so that only the water in here is being drained. And as it drains, it sucks this here. And now it's starting to pull water, which you can see is dyed green, out here. And it's kind of foggy because we have some condensation going on, but you'll start to see it fill up. As you can all see now.
Oh, yeah.
And what I'll do is just slowly start to fill up. So I'm going to check my time because I want to give 5 minutes to the suction cycle, 5 minutes to the pressure cycle, and go on from there. So it's about a minute. And I think I put some chlorine in here and whatever, and make sure there's not any algae accumulation. But I think there might be a little bit of that. And also there's a boundary layer effect that occurs because we have some small tubes. But with larger tubes, if you created an actual agricultural scale
There you go.
one, air leak. I'll talk about that too. If you have larger tubes, you won't have the as much resistance from the walls of this tube here. And also another thing that is good about having larger tubes and higher flow is that these check valves here, I've not yet been able to find a check valve that still does not leak. These are perfectly fine, but the thing is that check valves also rely on back pressure in order for them to close. And the problem is that the back pressure is so slight that this thing will slightly open and allow the air bubbles to go through here. So that's what was happening right now. That's why I'm kinking this tubing. So as you can see, the water is flowing down through here, through another tube, and falling up through here. And the reason why I have a condensation pump is that all the water that goes into this operating tank would normally go out on the ground, but I don't want to make a mess here or whatever, so I have this condensation pump that just pumps it back up into the feed tank. So, that's how we got.
Can I ask you a question, Mike?
Huh?
On the top right, what is that
Oh, this
one?
thing?
Yeah.
This is return.
Yeah.
When this tank here pushes up in here, I have this valve here to determine whether this can drain into the feed tank or not. So this would just be a return to go back into here.
Mm-hmm.
So I got this guy. It's filling up pretty good. Unfortunately, I think there was some algae accumulation inside the tubes or wherever, so it might be a little bit on the slower side, but as you can see, it's filling up. And now I'm just going to let that go. And let's see, actually it's just about done, so I can just, and also the air leaks too, I'm going to talk about this later on, about some advantages and disadvantages of the device. So it's about to go out. Right here, this is at a very low point. Eventually this will drain down below that bulkhead. You'll see the siphon disable.
Mm-hmm.
Right here.
How intense, like, do you have to be switching the pumps every 5 minutes?
You don't have to actually be here. This thing is actually automatically triggered by a triggering device, but in order for me to have more control over the thing and to be able to switch different things that would have to have an automated system, I just do it personally. And also it cuts down on the weight of things, and I don't have to build this giant apparatus for automatically controlling everything. And it's a lot more reliable in case anything is broken or it could stop something or whatever. So like just now is about to stop something. Okay, this is actually disabled while we're going. Okay, so that's all good. And then what I'll do for the pressure phase now. So I'll open this up. Actually, this was actually patented. I didn't realize it at the time, but there's actually a patent for a more proof Hydrautomat from 1927 or 8, where this thing will automatically purge with the triggering mechanism. So anyway, just open this up, and I'm going to close this cycle now.
Was the original design ever patented?
Oh yes, yes. It was filed in 1921. I think it was patented in either 24 or 6. Depends on which one. There's many different variations, even ones that use accumulators, and hopefully we'll have time for that. Or do ask me at the end of the talk. Okay, so now I just opened this up. This has been closed off. This has been closed. So now what's going to happen is that this is going to slowly fill up and push up the air, which is already bloated right now. It's going to push the air up into here. And let's see if I don't want these leaks. What it's doing now.
Do you want me to hold that for you?
Hmm?
Want me to hold that?
Oh, that's fine. No, and what it's doing right now is just slowly pushing the water. Oh, I see what's going on. Sorry. Air pocket. Yeah, during normal operation, you don't have to worry about that because these are all purged. That's fine. See how fast it's going now? Yeah, air pockets have always been a problem for.
In normal operation, do you have more pressure also with the water?
Oh, was it?
In normal operation, do you have more pressure with the water?
Yeah, normal operation, yeah, this would be flowing a bit faster, like in the toaster session, this is flowing a bit faster. But I think it's just been, things might have been accumulating in here a little bit too much. Yeah, by 7 or something. But as you can see, it's slowly pushing down. Actually, it's going pretty fast, because this is about an inch or so. This is about an inch right now. It's just been drained out. It's very subtle, but you don't really think much about it because it's so steady, but it's slowly filling up here now. Let's see what time it is. 1:37. Okay, making good time. Any other questions, anyone?
What are the agricultural applications?
What you can do with this device is you can have larger tanks, and you can string this out a lot further and pump this thing all the way up the hill, depending on what your head is. So basically, the positive pressure is dictated by, I think, what's called the Archimedes principle or whatever, which is basically just a difference in height. So the difference in height between where the high point of the feed tank is and the high point of where this operating tank is, that determines how much pressure there is to push water from here up to here. And the difference in height between this operating tank and the lower point of the siphon, that determines your suction.
So if you had, say, cattle pastures along a stream and the pastures went up a hill, you would be able to use the force of the water in the stream to then refill the water tanks?
Yeah, depending on the level of head you have, yeah, you could do that. You can also, there's many different ways also to talk about on how to boost the power of the device too. I think we're having an air leak or something that's going on. That's what I thought last night too, so.
I have duct tape in the car.
Now, air leaks are very hard to detect, unfortunately. But, so that's the basic operation of the device. Now, might as well just skip ahead to the advantages of it. Oh, all right, we're out of time.
Just briefly, you had said there is a way to build an automated system to stand in for what you're doing. What's involved with that? Is it a complex process?
No.
How would you go about doing that?
What you would do is, there's many different ways of doing it. Probably the very simplest one is maybe having a gate or some kind of system for opening and closing the valve. So if you're into electronics or something like that, you could do something a lot quicker, or you could have a kind of gate or something like that controlled by, it's like the there's many different ways. I have a pulley system that I invented, where when the siphon drains down into the, just drains downward, there'll be a tray. And what happens is the tray will be suspended from a pulley, and they'll have a counterweight so that everything can be relatively balanced. And what happens is the counterweight is like keeping it up, but when the tray gets filled with water, it becomes heavier, and it'll displace. And then the tray will be connected to a float switch that's inverted. So what happens is when it goes down, it closes, so that when the siphon starts to drain out, it'll close this valve right here, and it'll start the suction cycle. And then when the siphon turns off, there won't be any water to push the thing down anymore. So it'll go back up, and it'll close. I mean, it'll open. And then when it opens up, what'll happen is that it'll just start the pressure phase. So that's what I'll do with the pulley system. Thomas Gaskell Allen actually had a seesaw system for it. It's kind of like a lever with a counterweight on it. So you would have a little counterweight as a ball, and then you would have a tray that would get filled up by a siphon. And then on where the side where the counterweight is, that would go up when it gets depressed. That would be triggered by a lever to turn this on or turn this off.
One last question. If I'm just like an individual drop of water, what is my path from start to finish through the Hydrautomat?
Okay, I'll go from the feed tank. All right, so if like going from here to here, it's going from this point to this point to this point. And if it's from the operating tank, it's going from here to here to here. Because what happens is we'll use some of the water is used for power, and what happens is that as this water drains out, some of the water from here goes into here. So it's not a perpetual motion device, only part of it. Some of it goes up, some of it goes down. And some of the advantages of this thing, of course, is that it completely uses water. Sometimes it only requires water in order to run. It doesn't use gasoline, doesn't use electricity, it doesn't use moving parts. It also has a kind of a leg up on the hydraulic ram pump in that it is more efficient. In terms of the pressure used, it's actually 85% efficient. It doesn't use like shock waves like a hydraulic ram pump would. It's also like, as opposed to like a pulsar pump or a hydraulic ram pump, this thing can actually be scaled to many different ways. There'll be different ways of boosting the power, but actually I'll go over the advantages and disadvantages first, then I'll talk about that. So it doesn't use that. It doesn't use any of that. It uses a low amount of pressure in order to work, so it doesn't have a lot of strain. The things that you can use to build the Hydrautomat with they don't need to have high tolerance or anything like that. So you can build this out of a wide variety of different things as long as they don't leak. So it doesn't use any external, and it also doesn't use any moving parts, which is a major plus for this device. It's pretty much solid state because the only thing really doing the work is just the pressure in the tank. And because of the pressure, you don't have to worry about bearings wearing out, don't have to worry about vanes, don't have to worry about pistons, anything like that, nothing has to be oiled. The only possible thing that needs to be mechanical is typically the triggering system, although I'm kind of thinking of possibly designing a different new system that's completely pneumatic. Because all you would need is a way of turning off, of preventing the water from going from here to here. Because that's the only thing you need to do at the bare minimum to control this device is to turn this on and off at the right time. The disadvantages of it is that if there's any air leaks, if there's something like that, there's any leaks whatsoever, that does cut down the performance of the device. If there's a significant air leak in it, it will not run. So that is a problem. It's generally a stationary device, although you could make a portable version of this thing. It's not very hard, because really this is not an actual, kind of finished product sort of device. This is really an arrangement of tanks and tubing that can be made out of pretty much anything that is suitable, and it can be deployed just about anywhere. So the main uses of it, of course, is for agriculture. It's mainly used for irrigation. It's mainly used, you can also use it to supply water to a town or other place. You can run it through a filter or something and supply it to animals. Or you can also purify and use it for drinking. You can pop this to a high enough level, and you have a gravity supplied housing system too. I mean, that's the very basics of it. On my website, Msipos.info, that's Msipos.info, I-N-F-O. I have a large list of possible applications for this device, even going into desalination, because you can use the action of the waves going up and down instead of this thing filling up and down from the gravity. But I'll have to skip that for now. One thing you can, so now I'm going to go into the possible ways to boost the power of the Hydrautomat. Best thing to do probably is use what's called a pulsar pump, if anybody already heard of that. The pulsar pump's is probably the world's simplest water pump. It's a combination of a trompe and an airlift pump. And all you do with that, it's much simpler than this one, but it can't be scaled or anything. What you do is you would have water, you have a high point and a low point, just like this device, except the water would go from the high point to, say this would be the low point, this would be the high point. You would have a tank down here, and you would have a tube up here that collects water around the surface, so that when the water would fall into the tube, it would take some air down with it as bubbles. And it would run down into this tank here, and you would have another tube going out of the bottom of that tank to the low water mark, so you would have a continuity of flow. But the thing is that the air bubbles, by buoyancy, they want to go up. They don't want to run back down and then go outward. So what will happen is, say this would be the tank. Some of the bubbles will rise to the top, and also the water itself will rise to the top because of the equilibrium. So you have a combination of air and water going up through the tube. And what happens is that since there's a combination of air and water going up through the tube, the weight is displaced. So instead of the water going from here to just flowing back up to this point, it's lighter, so it'll go even higher. So you can just continuously pump water to a higher level with this device. And I've seen Brian White pump water in his backyard using this device with only like this much of difference in elevation, and he pumped the stuff like at 11 feet. It was absolutely amazing. He just shoots the water right up. And there's also a geyser pump, which is a little more experimental. I don't know what the performance of it is. I haven't seen much impressive results with it. But basically with a pulsar pump, if you can pump that to a higher level and then send this to the Hydrautomat, you have that much more difference in elevation to pump it higher. So that's one way, and the easiest way that I know of to make it, to get it even higher elevation from this device. Or you can just take it out laterally or whatever, it's just the height is probably the biggest obstacle to overcome. Second thing you can do is you could probably increase the tanks. I'm not exactly sure about the hydraulic intensification of it, but basically you have a difference in elevation that determines the pressure, and you can also play around with the dimensions of the tanks. I'm not exactly sure with hydraulics because I don't have too much knowledge in hydraulics myself, but if you think about each tank as a piston, what happens is that when one tank, so you have a larger tank that's being filled up or being pushed down on, well, if you could connect that large tank to a smaller tank and you're pushing up from that larger tank, that smaller tank will go up to a much higher level. Or if you push down from a small tank, you push down a small tank with a small amount of force, you can push something that has a lot more force but at a smaller increment in a larger tank. It's basic hydraulics, so that could also be used in some configuration, but it takes calculation. So I can't say it'll work that way every time. I don't know. Another one that's very, very amazing is this right here. Actually, you can use multiple Hydrautomats. So say this would be their high water mark. What you can do is you can take this right here and then feed that to another feed tank. So like this right here, you can actually run this higher. I just cut down to 2 tanks instead, but if you have 2 sets of these things, you make them higher. And then just string it out a full distance. Then what you can do is you can use the very highest tank as a feed tank. So instead of the feed tank being here or like the highest tank being up here, you can have a feed tank at the same level as your highest tank. And then the halfway point would be where your operating tank would be. And in each stroke, it would push it much higher than this feed tank and this operating tank could get it up to. So you could have it in multiple tiers, and technically you take it on to infinity, but it cuts back on your flow rate. Because you have to supply, every time you have a new Hydrautomat, like you see right here, there'll be one Hydrautomat, there'll be another one. You need to supply both an extra hoppering tank as well as supplying the next closed tank above it. So that's the ways of boosting the power. And I don't think we have much time left. I'm going to have some time for questions, of course. So probably a future project that's actually already been patented, but it's in the public domain, so you don't have to worry about anybody suing you for using whatever. The patent ran out probably 50 years ago, or 60, is to have like one or more operating tanks. And then what you could do is, instead of running it directly to the tank, to a closed tank where you pump things with, what you can do is you have what's called a hydraulic accumulator, which is just a tank for storing pressure. You can store positive pressure, which is pushing outward. You can store negative pressure, which is suction. You can have two of those guys, and you can have like multiple operating tanks all set up with check valves, so that only during a pressure cycle will it push into the positive tank, and only during a suction cycle will it pull from the negative tank. And from those tanks, those two accumulators, you can task it to each and every closed tank along the whole circuit. So you have multiple tanks here, and as long as you have a switching system, so you have like a high marker and you have a low marker for sensing, what happens is the tank will automatically detect when it's high or low, and then open up either the suction or the pressure, so that when it's high, it'll push it down, and when it's low, it'll push it up. But now it's a little bit more complicated, but it's already been done with mechanical means from the 1928 or 9 by J.O. Boving, who worked with Gaskell Allen in the Hydrautomat Limited, which was a company that made these things. So any questions, anyone? Yes?
The smaller tanks will have to be hermetically sealed, but the larger ones will be too hermetically sealed, or which of the tanks will have to be
Sealed. Well, the feed tank doesn't have to be, it's just a hopper. I mean, this is open to the open air, and it should be open to the air so it can, drain down. The operating tank, what happens is basically this is like a piston, is what this is. All this is a piston that uses water instead of an actual piece of metal going up and down. So this has to be sealed, and this has to be sealed. This can be open, and it wouldn't be such a bad idea for it to be open because it just wants to push down. And then when the next thing, you have like another one of these guys up here, or even higher, depending on how much distance you have. This is overrated here, but I just want to get a higher flow rate out of it. And also, something's going on in the system that's not making it as fast as it should be. But you have one of these guys over here, so that in the suction cycle, both this sucks up from here, and this will be sucked out to the higher tank. So all you need is a closed tank that's got the air tube connected to it, and this tank that has to be sealed, because you want this air not to, you don't want the suction being ruined by the atmosphere. Any other?
The length of the period, the 5-minute time
Yeah.
to switch, is it determined by the size of operating tank and the other one?
Yeah, it's both dimensions. I'm not 100% sure like what the thing is with hydraulics. It's very basic, but I haven't studied it very much. But it's a combination of both the dimensions of the tanks, but the pressures are mainly determined by the height. So, and basically like the size of the tank is more or less just the stroke length. But the thing is that the larger the tank is, the more the pressure gets displaced outward from it, so.
The stroke of the piston? The stroke of the piston?
Yeah, like how much air can be pushed up at a given time. So I'm not 100% sure though, but, any other questions?
You said there's a decent amount of calculation that goes in with something like
It's
this.
very simple, yeah.
I am terrible at visual approximations of elevation. Like if I look at that hill over there and I'm like, it might be 5 feet higher or 2 feet, I have no idea. So would you need to know the elevation of your land if you were to use a system like this to irrigate uphill?
Well, you would kind of have to like imagine, say if you have like a slope, you would have to kind of think of an imaginary line going direct horizontal axis and then dropping down, that would be your distance.
Okay.
It's really, like, I don't really have to do too many calculations.
That's what I was just,
When I
the laser.
came up with this design, I figured just like this distance equates to this distance, and distance from here to here equates from like how much this can go to here. But,
So you don't have to be
you don't have to be a rocket
extremely
scientist.
precise.
No.
That's
Mm,
good.
yeah,
No,
it's
you
very
don't have to be
forgiving.
precise. And honestly, it's really not too precise,
Oh,
this whole
forgiving,
system
isn't it?
here. It's kind of just, it's sort of a rule of thumb.
So all that water is connected, there's no section that's closed off?
What is that?
So I'm saying if the water in the tank, it goes through the whole system. So it's not like you could have like salt water from like tide water come into one thing and have that pump a different batch
Oh,
of
you
fresh
could pump
water.
different fluids with this thing. You could pump hydraulic fluid with this thing if you wanted to. Because what happens is instead of feeding this tank here from this, you can just have a bucket. My phone keeps on my ring. You can just, instead of like feeding this here from this here, you can just connect this tube to like maybe a thing of Hytran, whatever kind of fluid you want to pump. It could be just about anything as long as it doesn't erode what you have.
Right.
As long as that doesn't happen, you could pump just about anything with just water.
So you could use like your freshwater stream to pump your, say, your
Drinking water.
hydroponic solution.
Yes.
Okay.
Yep. Yep, yes, you can. There's many different advantages to this thing. I have a giant web page of just all applications, but the thing is that I only got through a fraction of them in an hour and 50-minute video. So it's very
Now,
long.
would the power of the stream be the same as that, as the device you have there for the power?
The power
I'm-
of the stream.
Yeah, to get the pressure going.
You know, this thing isn't really, it's mainly a hydrostatic thing, so
Okay.
you could have a very powerful river, but I wouldn't be able to exploit that from this device. But if you use like a Venturi or something like that, I was also thinking of something like that too. If you could use like either a Venturi or something like that, they'll just use the flow rate to create a vacuum or whatever. You could use a powerful flow of a river, for example, to cause the water to be sucked up to an even higher level. That can be done, just to get it started up. Or you could have that as an auxiliary power. I mean, you could possibly even replace the operating tank, you know, with Venturi. Who knows? I mean, it's all up to your imagination because this is just a hydraulic arrangement. It can be upgraded many different ways. It can be modified many different ways. It's all up to you. So, yeah.
Thank you.
Thanks. Oh, thank you.